Thank you very much. It's a big pleasure to be here. It's not working at all? It's not working. This is. No, but now it's not working. It's not
after switching it will, that light LED will go. Now speak.
Isn't it? Loud. So it is on?
No.
You hear me?
1 second. Hear it now.
Okay, we try like that.
Speak loud.
Okay, try to speak loud so even when it goes off, you try to hear me. It's a big pleasure to be here, and I enjoy this place. I think it's an enormous improvement with respect to 2 years ago, and it really is a great environment to work and interact. Sorry about the change of the title of my talk. I thought this talk would be more suited to the argument of the conference, and it concerns a large deviation. There is a result of a deviation. This is for the totally asymmetric simple exclusion. This is the joint work with CHEM side of Columbia University. And well, most of the people here may know what the totally asymmetric simple exclusion is. Just is the particle on zeta, the jump completely asymmetrically. So the particle from here jumps to here with rate 1. It depends from all the others, and there is exclusion when the particles try to jump. The particle is already occupied. You just suppress the jump. So there is nothing more simple than that. It's quite amazing how much study there is out of this incredibly simple mechanism. We will look more from the point of view of the surface, like an increasing path. This is blue, so this is a path that goes flat when there is no particle. Every time there is a particle, just increase by 1 this way. So you can make a linear interpolation, so you get the kind of trajectory which is continuous, and they have maximum derivative equal to 1. So with this, it's the same thing. I just like it to consider as a configuration space. It's not the usual one. Instead to make sharp angles, you make 45-degree angles. No, so in particular, this would be, so you have that there is a connection. The maximum increase will be eta x plus 1 minus x, will be between 0 and 1, and this is the quantity you may call eta x in the usual language of the particles, just 0, 1 if there is a particle or not. And there is a connection between the configuration. I'm not going to write it down precisely, but you have the mobility function, which is eta x1 minus eta x minus 1, tells you, well, just kills the jumps when there is the occupation, and the generator of the process. I just want to write it in this way. Sum over x and theta for a local function, t h x f h x minus f h. When hx is just the configuration h, where we add 1 in the point x. And then we always do some linear interpolation to get the continuous function. So this all goes, we want to see these after a scale, some bigger space, let me call E, the space of function h from in continuous function on R, which are Lipschitz continuous, and they are increasing, and H prime of X belongs to the interval 0, 1. Okay, so it will be positive, it exists almost surely the derivative, and it will be positive 0, 1. Cannot do more than that. And then you consider, you rescale space and time in this process in the same way, you scale space and time in the same way. So you take the profile H, you look at time at scale nt and space nc, where c is real, and you divide by n. Let's call this rescaled path h and t. And you have a dynamic limit for this, that h and t converge to h, so h and t. So this is a function, sorry, function of t and c. This belongs to E, to the space E of continuous trajectory that grows, and h and t c converge in probability to a function htx, which is the solution, the entropy solution of the Borg equation. The little index denotes the partial derivative in time or in space, in seed space. So H is the entropy solution of the Borg equation. So let me call this function phi of rho, the function rho 1 minus rho, just in case sometimes I write phi, sometimes I write rho 1 minus rho for convenience. So what does it mean that this is the entropy solution? Means that for any function h, convex, and C1, you have that this will be what we can call entropy. You can associate the flux F prime, the flux F, which is defined this time with the relation that the derivative of F is equal to H prime phi prime, and in a weak sense, the entropy H computed on HC minus F computed on HC, the time derivative of this and the space derivative of this, in a weak sense, this has to be negative. In particular, one can choose as H minus the thermodynamic entropy. Let me call S of rho the thermodynamic entropy, where S of rho is rho log rho plus 1 minus rho log 1 minus rho. The entropy solution is a weak solution such that this inequality is satisfied for any choice of an entropy function H in a certain convex form. F is a function that has to satisfy the flux of the entropy H, which has to satisfy this relation, where phi is this rho 1 minus rho. In analysis, they call entropy function, everything that is convex, they call it entropy. But don't be scared about that. But it's important that the thermodynamic entropy is an entropy. And in fact, that is what matters, I think. I'm sorry. Yeah, no, it's okay. Yes, correct. Yes. Sorry. Hmm?
I don't understand why you don't.
There's no stochastic term because in this scaling, the stochastic term disappears. This is a dynamic limit. This is what you call hyperbolic dynamic limit. And there is, if you just write down the Ito equation, the stochastic differential equation, you look at the scaling limit, you see that everything that the random disappears. And you just get a deterministic profile. The deterministic right has to satisfy this equation. There are various results. This was proven first by, I think, in '81 by Rosz, Rosz, and this was just for a very special solution, very special initial condition, the initial condition of the rarefaction fan. So here is full is equal to 1 is equal to 0, and then as time evolves, you get a solution which looks like that, which is the entropy solution for this particular initial condition. But the general proof was given by Rezan in 91, I think. Yes, 91. Always have trouble to write his name. Which gave a general method to prove dynamic limits using the attractivity properties of the exclusion process. And then I should also mention a work of Seppalainen of '98, where it was more clear the connection with the growth model, the surface growth model. Okay, so this was about the low large numbers, and then one can ask, is a low large number, particularly you can see this as a functional low large numbers. And then you can ask, what about the large deviations? And the first thing you should notice that, and this is the point, there are two scales of large deviation here. Scaling here. So you speed up time and you rescale also space. You rescale space and time in the same way. Since now you're rescaling time, h is growing also like n, so you have to rescale also the size of the otherwise it grows like n. So that's why you divide by 1/n. So this is right scaling to get something deterministic in the limit. Sorry, I should use different notation. This is just a particular configuration. Maybe I should mark it in a different color. And then I have used the notation I call h also the continuous function that you get in the limit. So now the deviation here, what can be caused? I want to see what the probability that in this convergence, H and T is doing something different. Something different, what could it be? Think about the Rosz case. It's very elementary to understand that there are two scales. You can see this as traffic jam. And the traffic, I mean, there is a first car who has all the space in front. If I want something different, I can just tell the guy, stop, and he will block everything. This will cost only n in time, with very, very little cost. To slow down things costs very little. But if I want to get something faster, it's not enough that I tell the guy to go faster, I have to tell a lot of guys to go faster. And this costs more, costs like n squared. So this makes you understand immediately why there are two scales of large deviation in this problem. So in fact, in Seppalainen, I think it was already proven that the probability that the height of the surface in the point 0 time t, when rescaled, the probability that stays less than this expectation by some factor positive alpha, this probability goes exponentially small, like e to the minus some constant n, of order n. It's just the slowing down of the thing. While in 99, I think, no, 2000, it was the seminal paper by Johnson, where it proves that the probability that HNT 0 is bigger than the expectation of Hn 0 plus alpha. That means we have speed up the process, we speed up the particle. This got like e to the minus n squared. And in this paper of Johnson, also there was a connection, the plastic width distribution that appears in this problem. Yeah, you have to speed n particle for times n, that costs n squared. To slow down, you just slow down one particle and, or finite. I mean, in the Rosz case, one particle. We'll see how to put a strategy to speed that, to slow down things. This is the derivative time. This is the kind of integrated Borges equation. This for the T, well, this is a viscous-less, there's no viscosity term. Is that what your question about? No, if it exchange back to space, I get the usual equation. Probably you're more familiar to see rho T equal rho 1 minus rho from a conservation law. Is that your question? Just because I'm looking at the yes. The classical Borges equation on the H. Yes, the derivative of H. No, the entropy is the weak solution not unique, but the entropy solution is unique. The weak entropy solution, I mean, the weak solution you can have many. In fact, in the Rosz case, if you keep this as if I stop the guy there and I keep the constant in time profile, this is a weak solution, which is not an entropy solution. The entropy solution is the one with the slope, with the refraction wave. But it's a weak solution. So you can see that in order to obtain a weak solution that is not the entropy solution, this will cost me an exponential minus a. So there is a general theorem almost proven by Jensen Varadhan. So the thesis of Jensen student of Varadhan, his thesis was of 2000. And there is a note of Varadhan of 2004. But it's not really a published article with a complete proof about this large deviation, but this describes how they give the complete description of this scale of large deviation. So in particular, they prove, just write a bit formally, that Hn behaves like some function g. Let me take a function g in the space, so such gt dot belongs to this space of increasing function. The probability that I have such behavior goes like e to the minus n, some function e, let me call ejv to distinguish from other one, where when in the usual sense of the closed upper bound on the closed set, lower bound on the open set to the logarithm, and so on. But the important thing is the rate function is given by the integral given to t in dt, the integral in dc. We take the thermodynamic entropy, so that particular entropy, S of rho, S of G of C, minus F, the corresponding flux, T, C, and you take the positive part, and you integrate this. So this will, so one can write it even more formally in the variational way, but basically it says if the solution, if the G, sorry, if this is okay, G is the weak solution. If G is a weak solution, maybe non-entropic. Otherwise, it's plus infinity on anything else. So, for example, if I take the Rosz case and I don't change the time, this is a weak solution. And this will have a probability which will be given by the wrong entropy production of this, or the wrong thermodynamic entropy production of this solution. And this is the price you pay. Otherwise, if you are looking for deviation which are not weak solution, the price is infinite at this rate.
This one with the noise in the equation, no? That the large
The noise is the dynamics. This jumps.
I'm saying that it's not for that equation plus noise.
This is a nonlinear equation, it is a deterministic equation. Probability Hn is the rescaled, to very right, is a rescaled profile. This is a stochastic profile and a stochastic evolution and rescaled in space and time. As n goes to infinity, converges to something deterministic, which solves, which is the entropy solution of this. So now I'm looking at the probability of this random variable, which is the profile in space and time of the exclusion, probability that follows this particular behavior, and there will be a rate function. The rate function is 0 if G is the entropy solution. Because for the entropy solution, this has to be negative, so the positive part is 0. And I know that entropy solution is unique, so has a minimum value. Different. There may be relations, but I don't know about large division for KPC. Capital T, just the time. Let's say G is for time t belonging from 0. Let's fix a maximum time, just a macroscopic time. Let's simplify. Let's not take time infinite. I want to see the behavior from time 0 to time t, which correspond to time nt on the macroscopic scale. Yeah, I want to see how they behave, the deviation. I want to see a different profile, and I want to see an evolution of this different profile, whatever it does. But the only way to have the Jensen Varadhan theory in particular tells me that this probability exponential minus n is only for weak solution of the thing. And one of the problems in this theorem, in fact, that there's not a generalization what weak solution is. Weak solution could be anything, almost. Or not anything, but it's hard to construct all the weak solutions. So, in fact, this theorem, the upper bound is the complete proof, I think, in the thesis of Jensen, and the lower bound is only done for profiles that have on shock. And I think it's still complete on the other side. So, but now I want to ask, what the probability that my profile behaves not like a weak solution, but like something else? In particular, if I accelerate the process. If I want to move it faster. And this is what our work. So what about large deviation for G not a weak solution? And this, as I said before, should have probability that goes like e to the minus n squared. Yes, because usually it's written for rho. So imagine that Gc is the density. G is just surface, so Gc is the density. Okay, so this is the usual. You go back to the usual form. Just wrote it in terms of the high process. No. There are many weak solutions. And there's only one entropy solution. So the Jensen Varadhan theory covers the deviation of a weak solution for not being an entropy solution. And the cost is the wrong entropy production, the wrong thermodynamic entropy production of this weak solution that is not the entropy solution. So now, what happened for large deviations that are not weak solutions? So that's what we prove. The theorem I asked, and let me mention P, that Hn behaves like some function G, where G is a generic function belonging to the space of D from 0 t into E. You give a topology on E, so you have a topology on this space, and this goes like e to the minus n squared, some other great function, E of G, in the sense that there is a large deviation principle. I don't want to spend 10 minutes to write down. Closed set, upper bound, lower set, lower bound. Open set, lower bound. So now to tell you what is the E of G. And I believe this formula is new. So you have the rate function for a Poisson process. The function of a Poisson process of intensity 1, if psi of lambda is lambda log lambda minus lambda plus 1. This is just the rate function if you want to see a Poisson process of rate 1, and you divide by t, and you want to say how is the probability that this behaves like alpha, for example. This goes e to the minus t psi. No, this to put a parameter. Sorry. T. And T over I. This goes like e to the minus T. Psi of alpha. Okay, so it's obviously equal to. Okay, so you have this function here, and then let me call C bar lambda just C, the bigger between lambda and 1, so just cut. So there are only deviations where lambda is bigger than 1, where lambda is smaller than 1 is just 0. Just slow it down, only the deviation where lambda, you accelerate, counts. And then I of g is equal to the integral from 0 to t in dt, the integral in dx of gc1 minus gc psi bar of gt divided by gc1 minus gc. And is infinite if gt does not exist. So it's finite only if time derivative in some weak sense exists, and then this is the price you pay for a generic deviation when you accelerate things. You can prove that this actually is a lower semi-continuous. They have a variational formula for it, and it's compact level set has all the good properties of a good rate function. How much time do I have? It's written there, okay. So, I really need to make some remark about this. One, you can see that this C bar, when this quantity here, gt over gc1 minus gc, is lower than 1, the price is 0. In particular, if you look at subsolution, gt less or equal of gc1 minus gc, the price is 0. So subsolution are a particular type of entropy solution. Entropy solution is a particular subsolution of or pointwise subsolution of the equation. So the region where, so in this case, E of g is equal to 0. This happens everywhere. So it's the only point is when gt, which is the current that pass through the site, is bigger than the mobility, then that's when you pay n squared. When you go below, you don't pay n squared. So the way this subsolution falls a bit in the limbo between the two theories. They are infinite price for the Jensen Varadhan functional, but they have 0 price for our functional, for our rate. But otherwise, there are all in the middle. There are all the particular things. So again, this means when you're the area where this happens, it means you are slowing down the traffic, and this is cheap. And the area where gt is bigger than gc, 1 minus gc, that's when you have to pay the price, n squared. That's basically the idea that is behind. And yes, the subsolution goes like I don't know, something between n and n squared. But as soon as I have region where where things are speeded up, then I pay n squared in the entropy price. So, so this was about it. Just maybe to comment. There is maybe the possibility to extend this, we haven't done it, to the open system. There was a paper by Bodino and Bernard in the RIDA, where they obtain the Jensen Varadhan theorem. They consider the system open with reservoir at different density, so you can have various regime of currents inside, and in that case, they consider actually the weakly asymmetric simple exclusion, and they can obtain the Jensen Varadhan theorem out of the limit for the symmetry. The weakly asymmetry goes to strong, to becoming a stronger symmetry. But in that case, when you want to prove that, they look at the current large deviation. If you want to prove that the current is higher than the usual current, it becomes infinite in that situation. I think an extension of this theorem to the open case should give the right rate function for this acceleration of the large deviation of the current in the open boundary situation. So, and then I can say something about the way the proof goes. Basically, but the heuristics I already said it, which one is. The other thing is, this is actually, if you take the process, if you consider the situation where you have, think about an finite volume, you just want to obtain a different, you want just speed up by lambda, the parameter. If you want to look at deviation of this type, linear type, let me say, a G of TXC, which looks like KT plus rho C, something linear in time and linear in space, which will correspond to constant density. But K will be the derivative in time and rho will be the derivative in space. Now, the only point is the parameter, what matters is the parameter lambda, K over rho times 1 minus rho. And you speed up. If lambda is bigger than 1, you take the process, the exclusion process that you speed up by lambda. And then you look at the relative entropy of this process with your original one. And you get this formula in the limit without the psi bar, doesn't matter because this will be bigger than 1. When this is smaller than 1, you're slowing down, you're slowing down the current, then that is not the right thing to do. Because it will be too pricey to slow down everybody. As we said, want to slow down, here will be enough to slow down one guy. So the idea is that you can actually reproduce, you obtain a process that reproduces your profile, just slowing down only in certain small region, let's say the region of size delta square, and in between, so here you slow down by lambda, and here you keep rate 1. And the distance here will be delta 1 minus delta, for technical reason. Then you see that doing it this way, you can do it in a way that the current is K, but you can obtain the profile that you want. And the price is 0 in entropy. And that's how you get, when you do large deviation, you must find the most efficient way, the most efficient strategy to obtain your profile. Here, the most efficient strategy, we learn it from the beginning, is not slowing down everybody, it's just slow down only a couple of things. This has a complicated construction to build up the lower bound, but the basic idea is this one. And I think time is over. Thank you very much.
So the strategy is that you give a small, so there's a small group of particles that you tell to
Slow
do
down.
slowing down, and they basically control all the rest.
Yeah, you want to control the traffic in the highway, don't tell everybody to slow down. That will be too costly. You can tell the first one, but that's too rough. You want to do something more fine because you want to construct certain density, not just block everybody. Then just tell a couple of people enough distance to, and it's less costly, and you obtain the same result thanks to the exclusion rule.
And everybody in between these positions, yeah, they're also automatically slowed down.
Because there will be, of course, you don't get a constant profile. You get something that oscillates. Inside you will get, even done the little graph. You do an explicit construction. Here you have something constant. And then, since there is a blockage, you will have a shock here, but then you will get something that goes like that, and then it goes back. But in the average, you get rho.
But all the particles there are moving at a sort of unusually large speed.
This will go at the usual speed inside, and this will go slow. You get something that oscillates, but remember that this large deviation only obtained in certain topology. So in the limit, you just see a constant. Even though in a certain mesoscopic scale, if things are oscillating, the limit will go to infinity. To the density you wanted. I mean, topology are important in large deviation. This is always a kind of a weak topology where you can always average on a small.
Because this corresponds to the situation where particles are moving faster than...
This corresponds to a situation where you slow down things.
And what?
I mean, when you go faster, it's relatively easy. You go faster, you just tell them, go faster. I know, I have GT, I have function G, I have a derivative in time, I have C1 minus C, so I know how much I have to accelerate them, this quantity. And I tell them, everybody do it. That's the best way to do it. But when you slow down, I shouldn't slow down everybody. I have to slow down.
You can slow, you can.
And I mean, the hard part is to get the bar here to really show that, in fact, the rate function is 0 when you slow down things, when you slow down the current.